Hi everyone. I think we're gonna just wait few minutes for others to be admitted from the waiting room, and then we're gonna proceed with our presentation for today. Yeah, please type in your name for the attendance purposes. So all right, I see no one else in the waiting room, so we're gonna proceed. So hello everyone. My name is Noura Basungul, a PhD candidate at the University of Michigan. Today we'll be talking about introduction to gamma detection. Sorry. Okay, we're going to talk first about the radiation detection process. So the first thing, of course, you have a radiation source. It could be either like a directly ionized radiation, such as alpha particles, beta particles, or indirectly ionizing radiation, such as gamma and neutrons. And once those radiation hits your detector or the main like measurement device, which is for our case is detector, it will start to interact with the material to form information carriers. And those information carriers will basically depend on the type of the material that your detector is filled with. So there are three different major types of detectors. The first one is the gaseous one, and hence like the information carriers for that type of detector would be electron ion pairs. And then the other type is semiconductors, and the information carrier is electron hole pair. And then the last category is scintillators, and the main charge carriers is photons for that case. And then after that, you will get a response, whether it's analog or digitized. And then after that, you will be able to do your post processing. And then based on the information that you are looking for and your type of detector that you have used, you can then use your response of the detector to get many different like information. For example, you can know the energy spectra, the amount of energy that's deposited by your incident particle or incident radiation. You can sometimes define the particle type, also the time of interaction and the type of interaction. So basically, as you have, for example, like an incident gamma photon for our case that hits, for example, a scintillator, it will start to interact with the detector material and then produce like light. And then that light will be converted into electrons, which will then be measured as a charge or a pulse of radiation that can be later on used for analysis to get your full pulse spectrum. So why we do need detectors in our life? So there are different like applications of detectors, and of course like you will apply detectors to those like areas whenever like you are using radiation. So the first application is for radiation monitoring and safety. For example, like for some environmental applications, you need to monitor the radium concentration. For example, in buildings, you want to make sure that it's below the limits that are set. Also, one other application is for monitoring reactors. So you need to monitor the power of the reactor and the distribution of the power with time, so you can make your decision based on that and based on the intended power of the reactor that you want to maintain. Additionally, there are also some sort of non-proliferation applications where you use detectors to detect if there is any special nuclear materials. Another application or area of application is you usually use radiation detectors for those measurements. And you need those measurements for sometimes in radiation therapy, which is one of the main applications that we need to keep track of the total amount of dose that's delivered to the patient during the radiation therapy treatment. Or even sometimes before starting doing the treatment to make sure that your treatment plan will work as it intended to do. Uh, the other application, which I'm sure like everyone who is dealing with the radiation has to have, which is a personal radiation monitoring device. And those devices are usually used to keep track of the total amount of dose that the personnel is getting during its interaction with radiation, so that we make sure that every worker is not exceeding the limit of the dose that's set for workers. The third application is radiation imaging, and this is also like one of the major application of detectors, which is in medical imaging. So radiation is used for some sort of diagnosis purposes to get images of the anatomical structure of the body, and also for sometimes for diagnosis of specific type of diseases. So detectors are used to collect those radiations and also to form radiographical images of the patient and hence helps in diagnosis. The other application, which is in radiography and non-destructive test, basically like X-ray that is the type of detectors, X-ray is the type of radiation that's used for that purpose. So we detect if any material has any cracks or any floats in the material, so we can decide whether or not that material is ready to use. So as we talked about why we need detectors, so we'll start talking about the different types of gamma detectors. So there are different types of detectors that are intended for usage for gamma detection, and detectors can come in different sizes, different shapes, and also the different type of material of each specific detector. So the type of the material that you used for your detection process will highly affect the type of the interaction that will occur with the incident radiation and hence the produced signal or the response of the detector. So as I mentioned previously, the first type would be gaseous detectors. As their name indicates, they are filled with gaseous material. And the first like type of detector that comes to mind once we mention like gaseous detectors is the ionization chambers and also the Geiger-Miller counters or Geiger-Miller tubes. And those are basically one of the main like sort of usage for those measurement purposes. The other type is semiconductors. Those are solid state detectors, and the major or the main type of detector that's under this category is the high purity germanium. And those detectors are well known for their high resolution, and hence they are implemented for high resolution gamma spectroscopy. The third type of detector is scintillators. Scintillators are scintillation-based material, so a material that produces light. And the main like type of detector under this category is sodium iodide, and they are known of having high efficiency. So we'll start talking in details, a bit like of detail about gaseous detectors. So this type of detection, so we'll talk a bit about the physics of detection. So as is an incident photon will hit the detector, it will start to interact with the detector with any of the three. There are three different like possible types of interaction that we already discussed in the previous lecture. So once the radiation will start to interact with the medium, will cause an ionization in the gas material. And that ionization will cause the production of electron and also formed like positive ions. And then by implementing electrodes, we can start collecting those charges, which will then cause the generation of electrical signal that we can detect. So as I mentioned, the main examples of this type of detectors is ionization chambers, survey meters, and GMTs. The main pros or main advantage of those detectors is that they are simple in their physics, they are cheap, and also easy to operate. The main disadvantage of them is that they have low Z material. And what a low Z indicates, or the relation of low Z, that means there is a very low efficiency, as there is a very low probability that your photon will interact with photoelectric absorption. A photoelectric absorption is a type of the reaction that will cause mostly like a full deposition of your energy of the photon. So that's what, if you have like a full deposition of energy, you will have full expression or full representation of the initial energy of the photon that interacts in your detector. So they will be much more suitable for gamma spectroscopy. However, like for this case, since it's a low Z material filled mostly with air, so there is low efficiency as there is low probability of interaction. So they are mostly used for low energy kind of applications. And we're gonna talk later about that as well. Moving to the next slide, sorry. Okay, we'll talk now about semiconductors. So the physics of semiconductors is a little bit different. So the charge carriers that are produced are different of type. So you have an incident photon that will start to knock out an electron from the valence band to the conduction band. And there would be like that gap energy that you need to overcome in order to remove an electron from the valence band to the conduction band. And hence, as an electron moves to the conduction band, it will leave out a vacant space, which would be mostly like which we usually call it a hole, and that will be probably like similar to a positive charge. So you can start then collecting that electron hole there that is produced, and then form your signal. One of the different examples of those type of detectors are high purity germanium, CZT, and also cesium X-ray detectors. One of the main things to mention is that the energy gap for semiconductors is a bit low, which is one electron volt. So it could be always mostly like less than 5 electron volt for the different types of semiconductors. And what that indicates is that you are going to produce many charge carriers, and that means less fluctuation, and also as a result will get like high resolution. This is like an explanation why those type of detectors has a considerably high resolution as they are compared to other types of detectors. So we'll start talking about the advantages and disadvantages of those detectors. So those detectors are mostly high Z material. So if you still like remember this figure from the last lecture, you see that as your energy of the photon increases, as your energy of the photon increases, and also like the type of the material, which is the Z, that defines like where exactly would be the most dominant type of interaction that happen. So for example, for low energy photons or up to around like 0.5, there is a high probability that you will be in the photoelectric effect domain as you have a high Z material. And also as you go to larger photons, you can have like Compton scattering effect or Baire reduction. So kind of a combination of the three different type of interaction could happen in those detectors, with higher probability if you have like lower energy photons to have photoelectric effect, which we mean by photoelectric effect, that's like the full deposition case. So as I mentioned previously, small band gap, which is nearly like 3 electron volt, will lead to the very high resolution of those type of detectors that could be as high as 1%. One of the main disadvantages of those detectors is that they are mostly limited to small sizes, and also they are considerably expensive. And one also disadvantage of them is that they become sensitive to the radiation damage. So if you expose those detectors for a long period of time to very high or intense radiation, they would be degraded with time after that, and the response would be affected due to the radiation damage. And also, the production of the electron hole pair is affected like thermally, so you will need to cool those type of detectors. So as for the case, for example, of the high purity germanium, you will need to do like nitrogen cooling in order to be able to collect the signal, and also like maintain our like a good production of the electron hole pair charge carriers. So we'll start talking about the third category, which is scintillators. So the main physics of scintillator, like generally, is an ionizing radiation that will hit the scintillator material and cause the production of light. And then light would be detected with photodetectors, which is like it could be like photomultiplier tube or silicon photodiodes that are used to collect light and then later on create the electrical signal. So basically, like the detector for like the scintillator case will consist of the main detector material, which is the scintillator, and then the photo detectors, which is the photo could be like photo, as I mentioned, like the photo BMT, which is the photo the BMT photomultiplier tube, or other types of photodetectors. So as incident radiation will interact in the scintillator, it will cause the generation of light, and that light photon will start to interact with the photocathode that is like one of the major parts of the photo detector, and then it will be later on converted, or it will be absorbed by that photocathode and then produces an electron, and that electron will start to accelerate and also multiply to produce additional electrons over the dinodes, and then would be later on detected with the anode, and then you will form the electrical signal. So there are two main distinct types or groups of scintillators. The first one is organic scintillators. So as their name indicates, they are mostly consist of organic material, which is hydrocarbons. An example of that will be the EG200. There is also like steel beams and plastics. The other category is inorganic scintillators, such as the sodium iodide, cesium iodide, and lysol. So we start talking about each category by like a simple comparison in between the two. So they differ first in the detection physics. So the generation of the light is kind of different from between like organic scintillators and inorganic ones. So for organic scintillators case, an incident photon will cause excitation of the molecule of the organic molecule to produce singlet and triplet excited states. And once the molecule returns back or de-excited back to the ground state, it will cause the release of visible light. And that's like your major like signal that would be later on detected. For the inorganic scintillators, so the main like type of charge carriers are electron hole pairs, so kind of similar like similar to the concept of the solid detector, except that the final produced signal is scintillation photons, not electron hole pairs. So for that case, you have your crystallets, and then with then excitation, you that electron will be knocked out from the valence band to the conduction band, and then the de-excitation of the molecule or of the electron back to the initial state will cause the production of visible light. So usually we use activators to kind of inhibit or add additional excitation states, so that like we can enhance the generation of visible light. So organic scintillators, so as I mentioned, the main material is hydrocarbon or organic material. They are considerably of low atomic number, so they have low Z value, and also they have low density that could be approximately 1 gram per centimeter cube. And this is like how some example of some of the detector shapes. Inorganic scintillators, on the other hand, are basically like solid crystals that have an atomic number that's much higher than that for the organic scintillators. and hence as a result they also have a higher density. And this is like kind of like different type of crystals that are inorganic scintillators. So we start comparing the main like advantages and disadvantages of each category. So for the organic scintillators, they're kind of cheap, and they are also can be made in different shapes, or so that you can achieve kind of like larger shapes. And they are also having the main advantage of being able to be sensitive to neutrons in addition to gamma. So they have the ability to differentiate between different types of radiation. One of the main cons is that they have poor energy resolution as they are compared to inorganic scintillators that could be around like 10 to 15%. And also they have lower light emission, which means lower efficiency. And then also the the photon scattering is the most dominant type of interaction that will happen in those detectors. And then there is a very minimal probability that you will be able to detect photoelectrical signal. So that means that you will not be able to record for full energy deposition events. Inorganic scintillators, on the other hand, has also the advantage to be considerably cheap, and they also have a better photoelectric absorption since they are high Z material. So they are much better, for example, than organic scintillators for good gamma spectroscopy, as you have like full deposition of energy. The other disadvantage of them is that they are also considerably poor in their energy resolution if we are comparing them to this semiconductors, which has like the superior energy resolution. However, they are a bit better in their resolution than the organic scintillators. One of the main disadvantages is that many of those crystals are hygroscopic, which means that they are affected by humidity. So just like a quick refreshing question. So what type of scintillators will you pick if you are aiming to detect gamma spectroscopy, or if you are planning for a gamma spectroscopy application, and why? So I'm gonna give like few seconds to think about it, and then we'll answer that question. Okay, I think you guessed it right. So the answer will be inorganic scintillators. For example, you can use sodium iodide. So why you will choose like inorganic scintillators, not the organic ones, because they have like higher efficiency, higher light output, and also better photopeak detection. And that's like if you are picking between the two types of the scintillators. If you are trying to choose between like the different categories, you're gonna choose the semiconductors as they have like better resolution. Okay, the second question. So what type of the scintillators you will choose if you are detecting mixed source of gammas and neutrons, and why? Correct. So you will choose the organic scintillators. Why is that? Because as we mentioned previously, that those type of detectors has the advantage of the pulse shape discrimination ability. What we mean by the pulse shape discrimination ability is that your detector will respond with different pulse types based on the different type of radiation that hits the detector. For example, as you can see, gammas has a lower tail if it comes like into comparison with the fast neutrons, which has larger decay pulse in comparison to alpha as well. So with that, with further analysis, you can easily differentiate between the neutrons and gammas if you multiply the total charge of the pulse. If you just like sum the charge, or there are different like ways to represent those or discriminate between the different types of neutrons. Different types of radiation. And that advantage of them is because like they have like a fast component, which is the rising edge of the pulse, and and the slower component, and that's because of the different like excitation for the singlet states and the triplet states. So we're going to talk briefly about the detector operation mode. So detectors can operate in two different modes. The first one is the pulse mode, and the second one is the current mode. For the pulse mode, each and every event that happens in the detector is recorded. That means you will get a full information about the timing and the amplitude of each radiation quanta that hits the detector and deposited like energy to the detector. So for that mode is of a specific like application if you are intended to do radiation spectroscopy, because you need the information about the full energy that is being deposited, the timing, and the amplitude of the radiation or of your event, which is directly related to the energy that is deposited by the quanta of radiation. The second mode is the current mode. So as you have like many successive events that may overlap with time, so your detector response would be pretty much like a signal that's dependent on time. So the response of those detectors is basically like a current. So you will get how that the total like signal uh, is affected like with time. And the specific application for that type of response of detectors is usually used for those measurements, as you care about the total amount of radiation that has been deposited in the detector, not the single and every like event that has taken like effect in the detector. And also this type of mode can also be used if you have a very high dose, a very high like rate of radiation, where it becomes a very overlapping events that can affect your final signal. So you would choose like this sort of mode. So I'm gonna just like review the gamma interaction and the detector response. So just to know how each of those interaction will appear as a response of the detector. So the first interaction is the photoelectric absorption. So the main equation that governs this interaction is that you have like what we usually care about is the total energy that's given to the produced electron, because that's like the secondary electron is what would be causing the response of the detector. So the main energy that would be given to an electron that's produced from the photoelectric effect would be pretty much like closer to the same initial value of the incident photon. It's just like minus the binding energy of the photon, which of the electron, which is a very, very small. So since you have like a distinct equation, that means electrons will pretty much have a distinct or a specific energy. So it will pretty much appear as a single photo peak, which is a peak that will appear at energy that's closer to the initial energy of the photon. For the case of Compton scattering, so the resultant secondary radiation is you will have your photon that will be then scattered, and also an electron will be produced. And the main equation that governs like the total amount of energy that will be converted to the electron is, as you can see, like from the equation, is affected by the incident energy of the recoiled photon, and it can range from like a minimum of 0 to the maximum of pi. So that means since you have like a range of energies that can be deposited by the secondary electron that's produced, that means you will have a continuum, not a single pulse. And that continuum will have an energy that's starting from the case where you have like a scattering angle of 0 to where you have like the maximum the maximum energy that can be transmitted to the electron for the case where you have a scattering angle of pi. And that like maximum signal, we usually call it like the Compton edge of your spectrum. Finally, you have the Baire production. For the Baire production, we know that the photon is fully absorbed, and then two Bairs are produced, which are like electrons and positrons. So basically, like the results would be a specific peak that's at energy equals to the main energy of the incident photon minus the mass twice like the mass energy of electrons, since you are producing like two particles which are equally in their mass, like the electron and the positron. So the total energy that can be deposited is approximately like equal to that like energy, your initial photon energy minus twice the mass energy of the electron. So suppose that you have a very large detector and you have like an incident gamma, what the detector response will look like, or the spectrum will look like. So as we mentioned, like we think about it, there are possible three different interaction that can happen. The photoelectric absorption, the probability is that like in gammas will be usually like escape from your detector based on the type of the detector. Otherwise, like the produced electrons are what's mostly like depositing the signal to your detector. Say for example, for the photoelectric absorption, I'm sorry, I'm gonna stop for a bit to turn on lights. Yeah, sorry for that. So you have the photoelectric absorption where you can deposit like the full energy that's like converted to the electron. So there could be like a full deposition. On the Compton scattering, you have your electron that could deposit up to its full energy, as we mentioned, and also there would be a secondary scattering photon. And that photon could escape or couldn't based on the size of the detector. Since for our case, we are assuming a very large detector, that means this photon will also deposit its energy in the detector, as if it could also interact by either like photoelectric absorption, um, uh, Compton scattering, and also their production effect as well. The final or the third sort of interaction that can happen also in the detector is the pair production. So you will produce two annihilation photons by the end of the track of the positron, and those two annihilation photons could escape also from your detector. That's based on the type of or the size of the detector that you are using. And since we are assuming a very large detector, that means that even those like photons will deposit their energy in the detector. As a result, so that means a very large detector will probably have a full deposition of those, of radiation, which means that the response would be just like one single full energy peak that's equal to the incident photon energy. Moving to the other case, which is the case if you have a very small detector. For a very small detectors, that means the different three or the secondary photons will always be able to make it out of the detector. So first of all, if you have like an incident photon energy that's less than the threshold energy of 1.022, which means that there is no probability that pair production will happen. So you have two main interactions. The first one is the photoelectric absorption, and since like the energy of the incident photon will be converted to that secondary electron that's produced, so electrons has a very high like stopping power. So there is a high probability that they will be stopped by the material. So electrons, as a result, will deposit mostly like full of their energy, and that would be represented by a single peak that's equal to the initial photon energy. And on the other hand, if a Compton occurs, that means the electron could have an energy that's from the minimum case where almost like no energy of the photon is given to the electron, up to the maximum energy of the electron, which happens in the head-on interaction. That's like for the pi scattering beam. This is like how your response will look like if your energy of the photon is less than that threshold. If you do also have the pair production effect to occur, that means your annihilation photons will make it out of the detector. That means you will need to subtract the energy of those, and then a peak will appear as well, since we know that like pair production will have mostly like a specific energy that will be deposited in the detector. And that peak, we usually call it double escape peak, because like both of the back-to-back produced annihilation photons will make it out of the detector. So for a more realistic case where you mostly have like intermediate size of the detector, there would always be a possibility that your photons will either like escape or will deposit their energy in the detector. So for the first case, if the energy of the photon is less than that threshold energy of 1.022, which is twice the rest mass of the electron, you will have your response to be like that Compton continuum in addition to the full energy peak. An additional feature that will start to appear, which is like that connection between like the Compton scattering and the photo peak, which means that you could also record some events that have energy that's larger than the Compton edge, yet they are less than the full energy deposition. And that feature, we usually call it the multiple Compton events. And why does that happen is that because you could have like multiple deposition of those, as your photon may interact like multiple times, and not like the produced like photon from a Compton scattering could also deposit part of its energy before it can escape from the detector. And that's why that will add into the energy that has been given to the electron with the previous like Compton scattering, and you would see that feature. For the case if you have like the annihilation, the Baire production event, you will have in addition like to the double escape peak, you can record a single escape peak, where you can also like one of the annihilation photons could interact, or possibly maybe by photoelectric absorption, and deposit like full of their energy in the detector. So the total response will be closer like to the initial energy of the photon minus that the energy of that annihilation photon that made it out of the detector. So this is like how the response will look like. In real world, there could also be some sort of material that surrounds your detector, and that also will cause the generation of additional like peaks or additional features that can be appearing in your final like response of the detector. For example, like an incident photon could interact with the surrounding material and cause like, for example, like the generation of photoelectric absorption, and then maybe that like that atom, as it gets like attenuated, it will return back to, like one of the electrons will return back to fill in that like that position or that vicinity that has been made with the electron that has been produced with photoelectric effect, and cause the production of characteristics X-ray. And those characteristics X-ray are a specific like feature of the different material that surrounds the detector. So you can start recording that peak, which is usually a low energy peak. Another type of interaction that can happen with the surrounding material is, for example, the Compton scattering, and then once again, like the scattered like photon could also make it to the detector and then be recorded by the detector. And for that case, as a representation of the electron that of the photon that comes from a Compton scattering interaction with the surrounding material, you will start recording the backscattering peak. And the backscattering peak usually like for like the largest energy that can be converted like to an electron, to an electron, for example, to be depositing like its energy inside like the material that it interacts with, there would be like a minimum energy that has been like given to the gamma photon that make it to the detector, and that peak will appear at mostly like half the energy mass of the electron if you do have like a very high energy like photon. And also some of the annihilation photons could also like make it after like the Baire production event, and could make it to the detector, and those has like a specific energy, as we know, which is equal to the rest mass of the electron. So you will start like recording the annihilation peak, which will happen at a fixed energy of 0.511. So The last thing I'm going to talk about is the energy resolution, since it's like an important feature of the detector. So you expect an ideal response of your detector to be a specific like spikes at the main energy that is deposited to the detector. But in real case, or in real world, there are different like inherent statistical fluctuations that can happen and cause the peak to have a specific width that's associated with it. So your deposition of energy will not occur at exactly the same value all the time. There could also be additional like sort of noise that affect the resolution um, or affect the accuracy of defining exactly like the main peak. So the larger the width of your spike or of the peak, the poor the resolution is. So if you still remember, a good example for a good resolution detector is semiconductors. They have a resolution of 1%, and also like poor resolution detectors such as scintillators could have a resolution of 5 to 10%. So we'll talk about the resolution. So the resolution is a unitless parameter that's calculated usually as a percent. So it's defined as the ratio between the full width half maximum of your peak divided by the position of the peak. So since like mostly peaks have a Gaussian shape distribution, they usually have a standard deviation of sigma, and we can relate the full width half maximum to be 2.35, the sigma that's from the Gaussian shape relation. So the resolution of an important thing also to keep in mind is that the resolution of the detector will vary with the energy, and also we need to account and implement for the resolution of the detector if we are doing like some sort of comparing like the measurement versus simulation, since like simulations will assume, for example, like your detector response to be ideal, so you have to implement or account for that to match like your results or to verify your measured results. So I'm going to talk like a brief example about resolution and how we calculate it. So the response of many detector is approximately linear. That means that you will always have a limit of resolution that's directly associated with the total number of charge carriers that are produced. And how that relation is driven is by as we know, like the resolution is the full width half maximum divided by the peak position. And then the full width half maximum is 2.35 sigma. And since you have linear energy response, you will have like the relation to be K multiplied by N, which is like that's like from the error propagation equations. And then you have like that linearity here, which is K multiplied by N, and you will be given like the final relation, which is 2.35 divided by the square root of the total charge carriers that are produced. So K will be a constant that's directly related to the detector type, and also N is the total number of the charge carriers. So if you are looking for a resolution of 2%, how many charge carriers you will need to achieve that resolution? I'm gonna give like few minutes to start think about it, and maybe if you have access to a calculator, start doing like the math. So I think some has already like done the math, so we're gonna maybe start talking about that. So you have your relation, which is the Poisson limit for the resolution that relates like the total number of charge carriers to the resolution. So you will identify that fraction of your resolution, and then just like doing the math, the final particles should be larger than 13,807. It's like oh 6 point something, but then like it's number of particles, so you would just like round it up. Yeah, and finally, just like a final image of what a detector response will look like in a real world. So it also like this figure is comparing two different types of detectors. So sodium iodide versus high purity germanium. So you can see like how the good resolution of high purity germanium. So it's mostly like it looks like a spike as if it's compared to sodium iodide, where you can see that like with that's associated with that. And you can easily calculate the resolution under each peak by just like using the information. So you already know the full width half maxima, just dividing that with the position of the peak, which is either like the 1173 peak or the 1.33 mega electron volt peak. So in summary, so we discussed the detection process, the different types of detectors that can be implemented for detecting gamma detectors. We talked a bit about the response of the detector and how it will look like. And we came to the end of this lecture. So I want to thank you all for attending this lecture. And I'm going to have any questions if you have, if I was able to answer your question. Otherwise, I think I'm pretty sure that we have many folks that are from the national labs who can help us like answering those questions. So we're going to have a great discussion. So it's kind of tough to keep track of the chat because there are many messages. So uh, okay. Um, I see a question for a CZT detector. So as its energy resolution is high, why we are going to measure the peak for this type of detector? Uh, I'm not quite sure, like I understood your question. So do you mean that why we care about the peaks if we are measuring with the CZT? Well, usually, like you care mostly about the full energy deposition, but you can also still get like it's kind of difficult to get the features if you have, for example, the Compton edge, because it will start to interfere if you are having like multiple gamma sources, or for example, you are doing like spectroscopy where you have more than one source. So it becomes a bit difficult to differentiate like the Compton edge, for example, to tell you, for example, whether there is that specific isotope or not. Photopeaks are good for telling you, for example, there is cobalt 60 by knowing where the photopeak exists. If you are measuring, for example, 1.17, that means you can easily tell that, okay, whatever I'm measuring, there is a cobalt 60 that exists in this, for example, unknown material of radiation. Uh, I'm not sure if I did answer like your question. If you have like if I didn't get like your question, maybe you can just like unmute yourself and yeah, just like say what do you mean by your question. Uh, there is a question also. Are activators are used for inorganic scintillators only? Uh, Activators are used for inorganic scintillators, and we are also introducing some sort of impurities for also semiconductors. So it's just like to decrease the gap so that you produce more like charge carriers. Uh, uh, what does dN divided by dE means in your graphs? Are you normalizing the energy? Um, I haven't talked about that, but you have your that's like the pulse shape. Sorry, the pulse spectrum. There is integral and differential pulse spectrum. So the dN by dE is the differential pulse spectrum, and that's like what it represents. It represents like all the counts that happens at that specific like many energy. So you have, for example, like some sort of energy bending, say like uh, point. Let me go back actually. Yeah. So say for example at that like specific position, which could have a bend size of around like say 1 kilo electron volt, and that means like the reading at that position means you have that number of electrons that sorry, that number of photons that deposited an energy that's equal to, for example, 400 in that specific energy band. That's like what it does mean, the dN by d. Yeah, I think I pretty much like covered all the questions in the chat to the best of my knowledge. So feel free to leave. Stop recording.